All right, so multi-step synthesis 4 is a reaction between tetraphenyl cyclopentadienone as well as maleic anhydride. And maleic anhydride we used before in experiment number 4, I believe. So that was with cyclopentadiene and maleic anhydride. It deals all the reaction. So that's exactly what we're doing in this one to make tetraphenyl 1,2-dihydrophthalic anhydride as well as carbon monoxide. After that, we're going to take tetraphenyl 1,2-dihydrophthalic anhydride and react that with bromine, elemental bromine, to make tetraphenyl phthalic anhydride, as well as two equivalents of HBr, hydrobromic acid. And that particular step is a is an oxidation step. Notice the in tetraphenyl 1,2-dihydrophthalic anhydride, it's actually not completely conjugated, but the product is. Makes pretty much a benzene ring. So recall that Diels-Alder between cyclopentadiene as well as maleic anhydride, shown here, was a shuffling around of pi bonds to make new sigma bonds. And remember, with a Diels-Alder reaction, we always form a cyclohexene. So one thing I want to point out above is that in the dihydrophthalic anhydride, that's not a cyclohexene ring, and it's because something a little extra goes on in that. So since it's a 5-membered ring, a cyclic diene, we have a bridged compound, and so remember that endo product is going to be desired just because of the stability of the transition state. We have a secondary orbital overlap with those carbonyls on the maleic anhydride. Okay? And I've highlighted the bonds in red that are formed, just to point that out for you guys. Alright, so now what we want to do is take a little look-see at multi-step synthesis 4's reaction between tetraphenyl dicyclopentadienone as well as maleic anhydride. So it's going to look very similar, with one little difference that's actually really important. Also, what makes this particular Diels-Alder really cool, in my opinion. I think it's awesome. It's super fun mechanism as well, so get excited. So we got the shuffling of the pi bonds to create that cyclohexene with the bridge. Okay. Oops, I accidentally wrote furan instead. We need to replace that oxygen with a C double bond O. And I also omitted the 4 phenols for clarity. Just make a note that those 4 phenols are still present in our desired reaction. So what we have here is the bridged compound that forms, but that bridge carbon actually has a double bonded O to it. So we want to make sure that we draw that on there as well. And then all the rest is going to be pretty much the same. So we have the endo formation of that maleic anhydride and the diene, Diels-Alder. Okay, so again, highlighting the new bonds formed in red. And so what you're going to notice is that that's not what the product is up above, right? But what I also want to point out is that CO, or carbon monoxide, is one of the products. Okay, so we have a CO portion there, and so we got a C double bond O with 2 lone pairs on that oxygen, right? So let's think about how can we extrude this carbon monoxide? Well, if we look at the Lewis dot structure of carbon monoxide, we see that it's a carbon triple bonded to an oxygen, as well as a lone pair on the carbon and the oxygen. Okay, so currently we have 2 lone pairs on the oxygen and none on the carbon. So if we use one of those to create that triple bond between the oxygen and carbon, we so carbon can't have 5 bonds, so we actually break that sigma bond and form a pi bond. That pi bond then shuffles around to create another pi bond, forcing the rest of the bridge to break, and those electrons from that sigma bond actually end up going to the carbon as the second set of lone pairs, or I guess the only lone pair on the carbon. But now if you just take a careful look at that CO, all of the carbon-carbon bonds have been broken, and so now that carbon monoxide can actually leave. And then if we take a closer look at the location of the electrons, we see that now it looks just like the dihydrophthalic anhydride product that we wanted. That's why I think this particular Diels-Alder, this reaction, this mechanism are really cool. So now what we want to do is take this particular product and do the next step of the reaction. So this particular reaction takes, or like the whole multi-step synthesis 4 takes quite a while. So the first reflux for that Diels-Alder takes 3 hours at least. The next reaction, this oxidation takes another 3 hours. So it's a long reaction. But that's not even including the analysis of the intermediates and the workup. So now that we have our dihydrophthalic anhydride product written, we have elemental bromine. So how does this oxidation work? So you might find a couple mechanisms, you might not. This is the mechanism I'm providing to you, and that the one that makes the most sense. So the lone pair on that bromine attacks the hydrogen. Those electrons create that last pi bond, creating more or less the benzene ring. And then the hydrogen, the carbon-hydrogen electrons now go to the other bromine, and that bromine-bromine sigma bond is broken. So what we form is the phthalic anhydride product. Remember, there are still 4 phenyl groups on this product that I omitted for clarity, and we also form 2 equivalents of HBr. Okay, so this is the mechanism that I want you guys to understand. This is like part of the reason why we needed to be so careful with our traps. And I'll mention a lot of this information, the safety data and stuff like that, in the live action video of yours truly coming up next. So let me know if you have any questions. I hope this clarifies everything that you need, and I hope you enjoy it as well. Today we're making a video of multi-step synthesis 4 since we can't make it to class next week. And so what we're doing is we're doing a Diels-Alder reaction with tetraphenyl cyclopentadienone and maleic anhydride. This actually results in the loss of carbon monoxide, giving us tetraphenyl dihydrophthalic anhydride, and then we'll oxidize that with bromine to tetraphenyl phthalic anhydride. And so let me just show you the setup. The setup is pretty much the same as the oxidation with nitric acid that we did for step 2. And so, but this time instead of a hot water bath, what we have is a sand bath. So we've got our power mites to allow us to regulate the temperature. And we want to just make sure that this reaction is going to be taking place at reflux temperatures with bromobenzene as our solvent. Okay. And then we also have our sand bath here. We've got a Claisen head adapter, and as well as our condenser, which has running water or flowing water. Obviously you can see the bubbles. We also are going to check for leaks before we move forward, and everything seems nice and tight. At the top we have our outlet adapter leading to this empty flask here. Okay, so this is similar again to the oxidation with nitric acid as a safety mechanism. And then we also have our trapping solution in this final flask here. So the trapping solution is again to capture any carbon monoxide, because as we know, carbon monoxide is poisonous. And that trapping solution contains copper chloride, ammonium hydroxide, as well as water. And so this is going to allow, the way this setup is, it will allow any gases evolving from the reaction to bubble through this carbon monoxide trap solution. If a vacuum were to form, the trap solution would get sucked up inside of this secondary flask right here, and so that's the purpose of this guy, just to prevent any of the trapping solution
from going into our actual reaction. Okay, and so now I'm going to go ahead and show you. I've already pre-weighed my 7 grams of tetraphenyl cyclopentadienone. So pretty. There you go. Also, 1.9 grams of maleic anhydride here, and then my 5 mils of bromobenzene. Okay, so first what we want to do is combine these reagents here. And so we're going to go ahead, I'm going to dump that into the funnel, our powder funnel, as opposed to our analytical funnel. I'm going to go ahead and make sure that is all inside the flask. And then I'll dump the maleic anhydride. So remember, in this particular reaction, it is a Diels-Alder reaction. So the maleic anhydride is our dienophile. And we used this in a previous experiment, and then our tetraphenyl cyclopentadienone is our diene. So before we add our solvent, we want to make sure that this is sufficiently mixed together. We don't want it just sitting like that. And so we actually want to just take a minute or two to mix this together really well. And because we only have about 5 mils of solvent and quite a bit of reagents, and so not everything is going to be soluble initially. And what we're going to see is, upon the application of heat, we're going to get like a nice brown solution. And that, in the end, obviously this is black. In the end, we want this reaction mixture to look more yellow, and we want the formation of maybe even a yellow precipitate towards the end. And that's going to be an indication that the reaction is proceeding as we would like it. Okay, and so I'm just going to go ahead and mix this together for a bit. I mixed that for probably 2 minutes, and I think that's sufficient. It looks like a nice homogeneous mixture of the two solids. And so now I did actually have, you might have noticed, I had a little bit of residue in this flask, or this beaker. And so I'm going to go ahead and put the bromobenzene in there first, just so I don't lose anything, because I want to maximize my yield. So if any of that does dissolve in the bromobenzene, I'll get it by that little wash that we're doing. And then same thing goes for the addition of the bromobenzene to the reaction mixture. So we've got that going. Now it's starting to turn like a nice purpley color. It's pretty. And I'm going to go ahead and mix this a little bit before I apply that heat. So I mixed this for about a minute or two, and as you can see, I mean, we still have a little purple color, but maybe it looks like a little bit more brown or even red. And I mixed it initially just to make sure we get everything in contact with one another, all the tetraphenyl cyclopentadienone as well as the maleic anhydride. And we can't mix with a stir bar because we don't have the normal hot plate. We were using a sand bath. And so we're going to occasionally, throughout the reaction, which is a reflux for 3 hours, and we are going to be taking it off of the sand bath and giving it a nice little shake, so that way we can make sure that we have sufficient mixing throughout the reaction. But other than that, we're going to go ahead and place this on the sand bath and turn the heat up and get that refluxing for 3 hours, and then we'll monitor occasionally and see how it goes. Hopefully we get a nice yellow precipitate at the end. Alright, so this is about an hour in, and you can see that we are boiling, therefore it is refluxing, and all this stuff came off the walls. It looks a little bit it's grape juicy. Kind of craving that now, so I'm gonna go ahead and get some. And then our trap, I saw a bubble a minute ago. Can't see it though. Oh, you see little something? No. Little
moving. 1 of 3 hours. Alright, so we are, oh man, hour 2. So, as you can see, we got some goobers on the top. No longer, it's definitely a solid, and it's no longer purple. Not that pretty color anymore. But that's good in this case because we are, that means the reaction's proceeding. So, cool. Yeah, can't really tell, it's dark. So far so good though. 1 more to go. Almost there. A little solid forming. Alright, so we're back in business. I had this reaction sitting here for a couple days just because I wasn't able to come and take care of it, but I was hoping that we would get some good news. And alright, so we're back in business. This is the dihydrophthalic anhydride, and what you can see is that it's no longer that dark, pretty purplish color. It's actually like a poopy brown color now. There's some colorless stuff, kind of solid on the upper portion of the round bottom. So we know something happened, right? So we're not going to isolate this particular substance. We're actually just going to cruise on through to the oxidation step. And so far, we're looking, there's no heat being applied to this reaction. It needs to be cool. And we have our water running. One thing that we did do, oh, look at that. So like, it's clear now. That copper just like turned completely clear. Nah, I'm just kidding. So the reason why that's clear is because now we have that bromine trap solution, and that bromine trap solution isn't the copper chloride mixture. It's actually a 2% sodium bisulfite. And so take a look at those hazards: harmful if swallowed, maybe harmful in contact with the skin, causes serious eye damage, and harmful to the fishies. So we want to make sure that we're properly disposing of this when the time comes. And so that's why this solution is clear now. I switched out that trap because we have different vapors now. We no longer have CO gas vapors, we have bromine vapors, because we will be adding bromine in bromobenzene for the oxidation step. Okay, so this stuff is gnarly. You can see that I have a couple mils in here, but this upper portion of it that's a lot of the bromine vapors. And so what we're going to do now is go ahead and add these 2 mils. I don't have my lovely assistant anymore, and so this is proving to be a little bit more difficult. We're gonna add slowly because this is an exothermic reaction. You might see a little bit of vapors. It's alright, we have it in the hood. Alright, that's that good stuff now. So go ahead and put the stopper back on. These vapors will be able to escape through our gas trap. They're going to go up here, through there, through this little secondary security flask, so that we don't get any of our sodium bisulfite solution in our reaction. And so those bromine vapors should actually just bubble through here, and so it'll quench those. Alright, I'm going to go ahead and secure that stopper with a little bit of parafilm and let this reaction kind of hang out for a minute, and then go ahead and get that reflux going for 3 hours. Alright, see you soon. Alright, so I went a little over. We're a little over our 3 hours, but you can see there's a little difference here. we've got what looks like some white crystalline. Looks pretty cool. Looks, I don't know, catch that Frozen 2 on Disney Plus. That's what it reminds me of. Alright, and so what we're going to do is go ahead and I'm going to lift this out of the heat and let that cool to room temperature and follow that up with an ice bath. Alright, so I got this guy hanging out on ice. I'm going to leave him there for about 10 minutes till he's cool. Just wanted to show you I had a little cork in there just to secure it. That way if the ice melts, it won't topple over, get water in there. He's secure on that cork. So I can probably just shove a little bit more ice all the way around it, but I'll do that. Okay. So I disassembled most of the apparatus just to give myself some room, but I have this guy right here, so I want to ask you a question. What should I do with it? Sodium bisulfite, can I just throw that down the drain? I want you to think about that for a second. So. Salt, right? So really important that we throw it in our waste container, because as you recall, this was harmful to the fishies, right? Also ourselves, but down the drain we care about the fishies more. And what we want to do is, let's see, macro scale sequence part 4, preparation of tetraphenylphthalic anhydride. That's us. Sodium bisulfite on there, and yes it is. So I can go ahead and out of my way. Perfect. So I'll go ahead and leave this right here for now. So now what I need to do is throw about 7 mils inside of this cooled flask. 7 mils of Ligroin. It's also known as petroleum ether, and little fun fact, doesn't have ether in it. Petroleum ether is just hydrocarbons, and they're different sizes, and so they will have varying boiling points. That's why the boiling point ranges from 35 to 60 degrees Celsius. We also can note that they're flammable because it is a hydrocarbon. It's an environmental hazard as well as health hazard. It's harmful and all that good stuff. So what we want to do now is go ahead and mix this up just to break up all the solid inside of them. So let me grab this my trusty spatula. So I'm just going to go ahead and chop this up. Let's see, it's breaking up. Yeah, look at it. Product. So I'm going to do this for a little bit, and then we're going to filter it. So see you soon. Alright, so I went ahead and mixed this up for a couple minutes, kind of breaking up the large pieces. And now what we're going to do is filter it off in our butane funnel. Okay, so here we go. Might take a little bit of work to get all of that solid out, but what we're going to do is also rinse about 3 times with 2 to 3 mils of Ligroin. So I can use that as a means to get this out, but what I want to do first is just get as much as I can out with the spatula. And then we'll resort to rinsing with Ligroin after that. To swirl it around just to get everything in suspension, and then once it is, this is going to be the last wash for me. See if I can get any off the wall. So the cool thing about this guy is that you can bend it because it's really soft metal, and that allows you to scrape things off of round bottoms like this. Fancy, huh? Check that out. Boom. And the things you learn in quarantine. Alright, so that's probably cool. We're gonna go ahead, swirl that, get it in suspension, and then dump. We left a little bit behind, but there's a lot in there. Oh my goodness. There's quite a bit. So let's take a look at this. So now what I want to do, I'll let this dry just a little bit. I'm going to break this up, because the next portion of the experiment is, since it's kind of chunky, what we want to do is transfer it to this beaker, and then we will kind of chop it up even more, and then we will add 15 mils of Ligroid, and we're going to heat that up on a stir plate, and then kind of clean it out. It's not a recrystallization, but we're heating it up to get any of the either impurities or starting materials out of there. And our product is not soluble in Ligroid, so that's why we're able to do that. So let's go ahead and transfer this to the flask. Alright, so we got our beaker here, and I'm going to transfer this solid in there best that I can. Let's see if we can break some of this stuff up. So it's kind of caked on there, so just free some of that up. That in there. Just a little bit more. I don't know if you can see that in the camera, but just a little bit more. We had quite a bit of product after that reaction, so I'm not too concerned about every little bit, but there we go. So now what I can do is transfer, or about 15 mils. I'm going to go ahead and mix this up. Trying to get those chopped up. Those big pieces need to be broken up, just in case we have any impurities or starting materials of any sort hiding in there. That's the purpose of this step. We're going to be heating it as well. That's going to help with the process. So I already have this stir plate hot. So we want to make sure that we're stirring constantly while we're doing this. So that way our solution doesn't pop or like explode, kind of. Sometimes when you build up some surface tension, it finally starts to boil and then it just pops up and flies everywhere. So that's why you always want a stir bar or stirring rod, or in this case we're going to be using our spatula. So whatever you gotta do. You can see a little bit of boiling here. So I'm going to take that off because I don't want it to overheat. Okay. It looks like we have a nice fine powder now. Looks like a beach sand to me. You get a little closer look. You can see some of that solution at the top is brown. And so we're going to cool it just in case any of our product is slightly soluble. Right now we're not really crystallizing or anything, so it's fine if we just throw it right back in the ice. And plus the glass is it's strong enough to handle that hot-cold transfer as well. So it's just going to hang out there for a couple minutes and then we'll repeat the process. Alright, so now it's been hanging out for a minute. You'll be able to see this brown solution on the top. I'm just going to decant this off. Slowly pour off only the top. I'm only pouring in here just because I have my other leg going at the bottom. So this is pretty much my waste container. But now I'm just going to add another 15, heat it up, and filter. Okay, so I'm going to go ahead and clean that up before I add the Ligroin and heat it up. What I'm going to do is set this up so you guys can see me transfer. Basically, I'm transferring into this pre-weighed beaker. And then just to get a crude yield, and then we'll go ahead and do the crystallization after that. It's not super dry, it seems. So our crude yield might be a little off. I mean, the Ligroin is pretty low boiling, so vacuum for 10 minutes should be sufficient. And a little knock and knock. Yeah, let's see what this guy weighs. You guys gonna help me remember this? Goes the dynamite. 6.951 grams. Alright folks, so 6.951 grams. The crystallization method is with benzene, and we need about 8 mils per 1 gram of product. So I'm gonna go ahead and set that up real quick and then we'll do the recrystallization. 25 mils in here, measured from my 25 mils graduate cylinder. So I'm going to go ahead and, so it had almost 7 grams.
which means that I'll need close to 56 milliliters of solvent. I've only measured about 50, just because that was an estimate. So what I want to do is put about half of that in first, and get this on the hot plate. And remember, you don't want to heat your solid material until you have solvent in there. So sometimes this could result in something called oiling out, and once you form an oil, it's pretty tough to get that good stuff back. So that's what I want to do. Just make sure we get this guy heating up. He's heating up. And remember, the goal for crystallization is to add the minimum amount of hot solvent to dissolve your solid material. And the reason why this works is because typically most things, most solids will be more soluble at higher temperatures. So if I dissolve all of my material in the minimum amount of hot solvent, as it cools down to room temperature, it no longer has that same solubility ratio. So as it cools down to room temperature, it will start to crystallize out. If I allow it to go slowly, it'll crystallize out. If I force it too fast or kind of fiddle with it too much, it'll end up basically give us microcrystals, and it'll look like more like a precipitate rather than a nice pretty solid, a nice crystalline solid. Let's see, so there are signs of boiling, so I'm going to add a little bit more. I only added about 10 or 15 mils, so let's see. That's going to do it. Make sure that everything is pretty hot. This guy. Let's see what it looks like. What it look like. I saw a bubble. I like when you have a liquid on the top, and then it's like fireworks. So pretty. Alright, we're going to go ahead and dump all 50 mils in here just because my intuition tells me we'll need more. That's bad. I wasn't stirring it sufficiently probably because I was looking at the cool fireworks. Sometimes chemistry will do that to you. So let me take this off the heat real quick, just to get us more. Have it all dissolved, but what I want to do, put quite a bit in there, so what I'm going to do with those stubborn pieces is just get those out of there. So I'm going to do something called a hot filtration. That's going to be just filtering it while it's hot.
let that cool to room temp while I clean up. Alright. Let's see, this is probably room temperature. We do have some crystals on the bottom. Inside I kind of see like a little crust. Let's see if that focuses. There you go. Yeah. So I'm gonna leave that in the ice for a bit. Not a ton of product, but this reaction is ready to make it. So here we go. We'll leave that in there for 10 minutes or so, and then we'll filter that out. Alright, I've had about enough of this, so I'm gonna filter this guy out. Looks like most of the stuff is stuck to the wall, so when I pour it, it will just filter it real quick. Most of the solid will get stuck at the bottom. There you go. So I'll go ahead and scratch this off, filter the rest, and then we'll take a look and see how much we get. Solid in here, but we got product in there as well. Sorry, the lighting can't even. It's actually really pretty. So yeah, we're gonna go ahead and weigh this. See what spilled some, and I spilled some other ones. Happens to the best of us.